same amount of force on you is very small. Therefore, the acceleration on the Earth is significant, but it can barely affect the motion of the sun because the sun is so massive. It is the same as when we are doing with projectile motion, we throw something, and we assume this frame we are in right now is an inertial reference frame. But like when the gravity of Earth pulls this chunk is also pulling Earth with gravity. But you don't seem to feel the Earth moving because it's so massive. Acceleration of the Earth can be negative, and we can treat the acceleration of the sun can be negative, and we can treat the sun's frame as an inertial reference frame. Okay. Now, when the Earth is moving in a circle, you have done your homework, and you know you need an acceleration going to the center of the circle, and that acceleration will be v squared over r. Let's call it r12, and the mass of the sun is m2. The mass of the Earth is m1. So r12 is the distance between sun and the Earth. Okay. Yeah. So
I just want to make sure. So it is a inertial reference frame.
It is approximately an inertial reference frame.
Okay.
As long as the mass of the sun is way more bigger than the mass of the Earth.
Okay.
In fact, it is like, so the mass of the sun is a lot bigger than the Earth. I have the value in my textbook. I have to look it up. So the mass of the sun is 2 times 10 to the 30 kilogram, while Earth is just 6 times 10 to the 24. They are off by 6 powers, so that is a million times difference. The mass of the Earth is a million times smaller than the mass of the sun, so we can get the acceleration of the sun. Okay? Good. All right. So F equals ma. Let's write down the vectors and actually see how we're going to apply it. The way we apply it is to not write it as vector again. We write it as vector just to save chunks, but when we're applying it, we're still dealing with numbers. So we write it out as fx equals max and fy equals may. Now, the gravity is attractive, so gravity should be going inward. And when I look at this time instant, when the Earth is passing through the x-axis, this gravity should be horizontal. So there's no y component of force on the Earth. Okay? The force on the Earth right now only has x component. That's why I choose this time instant instead of the time when Earth is up here, because then I only need to deal with one equation. So we can just ignore this one and use the x component of this equation. Now, gravity is going in negative x, so it's going to be negative Fg. Fg is the magnitude of this force, so it is positive. And to represent this vector, the x component is negative because it's going to negative x. So to follow the rule, I need to write it as negative g, Fg. But the acceleration is also negative because it is accelerating to the center of the circle. So here, I also have a negative a. A is the acceleration of circular motion. And you see the minus sign will cancel. So far so good. Okay. Now, gravity should be proportional to their mass and some power of their distance. So we can plug it in here, m1, m2, and distance to some power should be proportional, not equal, because we don't really know what constant is in here. It is proportional. So this should be gravity, which is proportional to this, so they are proportional. And I'm going to put the acceleration of circular motion here to relate the speed of this motion with the gravity. Okay? I substitute A equals this into here. Any question? Remember what we're trying to do here. We want to find out what is n, like what power of distance should gravity be proportional to. So we want to find something we can measure experimentally. Speed is something we can measure, but it will be easier if we turn it into the period of this orbit. We can easily see how long it takes for this planet to go around a circle. On Earth, that will be 1 year, 365 days. You guys know that? Good. So let's try to turn this into orbit, into the period of orbit. If the speed of Earth is v, then the time it takes to go around that circle will be the distance, which is the circumference of the circle, divided by the speed. Is that good? So you get speed, or I should just say the speed should equal to the distance it travels by the time it takes. Alright? Now, in this relation, we have b squared, not b, so let me square it. B squared should be the square of that thing. 2 squared will be 4, pi squared will be pi squared. R12 squared will be R12 squared, and t squared will be t squared. So that should be another way to represent the speed of the Earth if it is going in circle. So I can plug that in here. And this is the mass of the Earth because I'm looking at the acceleration of the Earth.
Why
Yeah,
do you
easy.
square everything?
Because I have the square of v. So I want to look at v squared. And to square it, you need to square everything.
Yeah. Okay.
So here you see, because gravity is proportional to both their masses, and we are looking at the acceleration of Earth, the mass of the Earth will cancel, so the mass of the Earth does not affect what we're going to calculate later. And we get that the mass of Sun divided by some power of their distance is proportional to v, which is this thing, v squared. V squared is this thing. And divided by R12. So let's divide it by R12. Okay? So now let's move t squared to the other side. And all the other things to the right hand side. We still have 4 pi r squared. If I move m2 to outer side, it goes to the denominator. And now I am going to count how many R12 I have, how many power of distance I have. There's a distance, there's two distance, so they cancel, and there's only one distance in denominator. When I move this R12 to the other side, denominator becomes denominator because what I'm doing is multiply both sides by R12 to the power of n. And there's still one more here, so it's power to n plus 1. Okay? So at the end of the day, the period of this orbit square should be proportional to some power of the distance. And the far away our Earth is from the sun, the longer the period is. So 1 year will be longer if Earth is far away from the sun, and it will be shorter if the Earth is closer to the sun. That is very true, because if you look at the period of, let's say the Mars, if you look at the period of the Mars, it will be so the period of the Mars, which is far away from sun, is 687 days. A year on Mars is longer than a year on Earth because it is far away from the sun, so its period should be longer. And if you look at the period of Mercury, Mercury is the planet that's closest to the sun, it will be a lot shorter. The orbit of Mercury has a period of only 59 days. 2 months on Mercury and then you're done. That's 1 year on Mercury. That's 2 months. Okay? So now, we know if the distance from the sun is longer, the period or the time on 1 year of 1 year on the planet will be longer. But if we want to figure out exactly how big this n is, we need to